Instead of needing a coat for each season, imagine having a jacket that would dynamically change shape so it becomes more insulating to keep you warm as the temperature drops. A programmable actuating fiber developed by an interdisciplinary team of MIT researchers could someday make this vision a reality. Known as FibeRobo, the fiber contracts in response to an increase in temperature, then self-reverses when the temperature decreases without any embedded sensors or other hard components. The low-cost fiber is fully compatible with textile manufacturing techniques including weaving looms, embroidery and industrial knitting machines, and can be produced continuously by the kilometer. This could enable designers to easily incorporate actuation and sensing capabilities into a wide range of fabrics for myriad applications, such as programmable compression garments that could aid in post-surgery recovery. The fibers can also be combined with conductive thread, which acts as a heating element when electric current runs through it. In this way, the fibers actuate using electricity, which offers a user digital control over a textile's form. For instance, a fabric could change shape based on any piece of digital information, such as readings from a heart rate sensor. The research will be presented at the ACM Symposium on User Interface Software and Technology. Current shape-changing fibers have pitfalls that have largely prevented them from being incorporated into textiles beyond laboratory settings. One fiber, known as a shape-changing alloy, only contracts by about 5%, doesn't self-reverse, and often stops working after a handful of actuations. Another, called a McKibben actuator, is pneumatically driven and requires an air compressor to actuate. The MIT researchers wanted a fiber that could actuate silently and change its shape dramatically while being compatible with common textile manufacturing procedures. To achieve this, they used a material known as liquid crystal elastomer (LCE). A liquid crystal is a series of molecules that can flow like liquid, but when they are allowed to settle, they stack into a periodic crystal arrangement. The researchers incorporate these crystal structures into an elastomer network which is stretchy like a rubber band. As the LCE material heats up, the crystal molecules fall out of alignment and pull the elastomer network together, causing the fiber to contract. When the heat is removed, the molecules return to their original alignment and the material to its original length. By carefully mixing chemicals to synthesize the LCE, the researchers can control the final properties of the fiber, such as its thickness or the temperature at which it actuates. They perfected a preparation technique that creates LCE fiber which can actuate at skin-safe temperatures, making it suitable for wearable fabrics. Researchers had been unable to accomplish this with other LCE fibers.